to get a picture, to get your own picture. So I'm going to try to do that here. Here is my y-axis and my x-axis, something like that. Where does cosine start?
0, 1.
0, 1, that's right. So we do the typical cosine, maybe it looks something like that. And this would be on the interval from 0 to pi over 2. Like so. Okay, so let's see if we can get some stuff kind of put in here, like some things we talked about in the video, things I talked about in the video. We're going to be revolving this around the y-axis. And so I usually just make a note for my own self, just that little arrow, circular arrow saying, hey, the y-axis, that's my axis of rotation, or my axis of revolution. So I can ask you guys to do this mentally. Like I said, in the coming days, we'll do this with other things. If we have time, we hardly ever do. I think food is a really awesome object lesson for shapes that get generated here. There's a lot of good foods that help you see things like this. But anyways, maybe like as you mentioned, maybe this class particularly would be bad timing for that, as far as lunch and all. Yeah. So guys, principle number 1. Hey, big takeaway that you have to get, if you didn't get from the video, you didn't retain this, you got to take this away today. The representative element, representative rectangle or disk, depending on how you want to talk about it, has to have what relationship with its axis of rotation? Perpendicular. Good. So as I draw this in, my representative element, it's got to be perpendicular to the axis of rotation. So it needs to look about like that. And I just want to point out that if you just like took that little representative rectangle and you did rotate it around the y-axis, then you would get literally a disk. It would look something like this. And the y-axis would be right through the middle of it. It would come in like so, and then like so. You represent it. See if you can, I hope you can see this amazing 3D view. Can you guys see the rectangle in there?
Yeah.
And so all we're really doing here is we're taking these disks that would show up if we partitioned this off into rectangles and rotated them. And we're saying, what if the thickness of the disks was heading towards 0? That would make the number of disks go up towards infinity. And if that were the case, the limit of this expression would give us the actual volume of that figure. Make sense? If you were going to describe this, the 3D figure, can you picture this in your mind? Kind of like based on what you saw in the video? Well, how would you describe the resulting figure? A dome. Okay, I like it. Any other descriptions? Spherical, sort of-ish bullet. Yeah, a little like a blunt. Instead of like a really pointed one. Or you say bullet?
That's not a different. He's a ham.
Ham? Yeah. Half of a ham? Or whole ham? Oh. So it'd look like...
In terms of why.
Like that kind of? Yeah, okay, I got you. I like it. We'll go with food again. It's good.
Make this in terms of why, right?
We will.
All right,
Yep.
so, okay.
Okay, so guys, let's get back to details here.
Would this be calculator active?
Maybe. Depending on what you're asked to do. Maybe based on the question, yeah. So then here is the next most important thing. So big takeaway number 1 is the axis of rotation and the representative rectangle have to be perpendicular to each other. So the axis of rotation we told you, so you need to establish your representative element to be perpendicular to it. This also sets in motion basically the whole rest of the structure of this. What is the thickness of that disk? dx or dy? It's measured on the y-axis, so it's a dy thick representative rectangle. What that means is that everything in your integrand, everything as part of your integral is going to have to be in terms of y. So what this does now is basically tells me that I'm going to have integral of something or other dy. I've got to figure out the details. So as far as the details go, the limits of integration maybe could come next. Just like when we did areas, if you've got a horizontal representative rectangle, the accumulation is from bottom to top. So when we think about how we're going to accumulate, the accumulation is going to start down here at the bottom, and it's going to end up there at the top. So where does it start? And where does it stop? 0 to 1. The temptation would be to use that 0 to pi over 2 automatically. Those are x coordinates, right? And this is going to be in terms of y, so we're going to be using y coordinates for our limits of integration. So these are the big takeaways. I want to review these again and give you a chance to ask a question if you need to. So big takeaway number 1, representative element has to be perpendicular to the axis of rotation. Big takeaway number 2, that sets up your dx or your dy. Number 3, I'd go with my limits of integration, in this case accumulating from bottom to top. You guys have any questions so far? Go ahead, Alexis.
How'd you get the 1?
Say again?
How'd you get the 1?
How'd you get the 1? Yeah, so the 1 is going to be, so like we got to accumulate from the bottom, which is the origin essentially, right? It's going to be the x-axis there. So 0, how high does this get? Well, that's going to be essentially the y-coordinate when x is 0. So right here. So if you wanted to, you could write it out as y equals cosine of 0, and cosine of 0 is 1.
Okay.
And so you'd stop up there at 1. So, yeah, I think if you're unsure about that, I would just plug in and realize that basically the accumulation stops when the region stops, and the region stops at the top of cosine. You could also think, hey, cosine has an amplitude of 1, and so it goes from a center line of 0 up to a high point of 1. You can stop there. I mean, so you wouldn't necessarily have to plug it in to figure that out. You could do it that way too. Any other questions? There are no tiny, insignificant, bad questions. They're all good. Okay, fair enough. So then, of course, what goes in here is pi radius squared. Remember from the video, essentially this is just little skinny cylinders being accumulated over and over and over again to find the volume of these shapes. So it's pi integral r squared. The radius is going to be from the axis of rotation out to the outer edge. And this is what we're going to do. I can't remember if I did this in the video, to be honest with you. We're going to do a little bit of like theoretical foundational work here. So if I were to ask you, how far is it from this purple dot to that purple dot, what would you say? So say again? I don't think so, because isn't this a horizontal measurement? Does that make sense? The thickness, yes, I'll give you that. But I'm talking about this distance. I'll try to illustrate it here a little better. I'm talking about that distance right there.
The cosine of something a little less than pi over 2.
You're going too far. Say again?
X minus pi over 2.
Going too far.
Pi over 2.
Going too far. I'm going to just call it x. Let's think back to what this means. Think back to your pre-algebra days. When you first learned about the Cartesian coordinate system or the rectangular coordinate system, didn't they basically teach you that if you start on the y-axis and you move to the right, we call that an x distance, right? Or if you start on the x-axis and you move up or down maybe, we call that a y distance, right? So literally, if you start on the y-axis and you move to the right or you move to the left, that's simply an x distance. And maybe the better point here also would be to say that has to be a variable, because depending on where you are, and this is kind of where you guys are going with this, over there like Ben and Noah, depending on where you are, that x distance changes, doesn't it? I mean, down here at the very bottom, it's pi over 2. Up here at the very tippy top, it's 0, and it hits all the points in between, because we have a continuous function here. Hits all the points in between as you journey along that path. So, if you wanted to, I think this is definitely bad form, and it's definitely incorrect. I wouldn't give you full credit for this. But couldn't you say this? The radius is x. With a domain from 0 to pi over 2, right? It could be any number between 0 and pi over 2. That's bad on a number of levels. Number one, primarily, that needs to be a y, doesn't it? It's got to be a y. So how could I replace that x with something that only has a y in it? Yeah, there we go. I know from before that y equals cosine of x. So then how could I then transform that to being x in terms of y.
Inverse cosine.
Inverse cosine of both sides. That would give me inverse cosine of y is equal to x. So then instead of an x in there, I could just put in inverse cosine of y. Now, as far as, I think your question earlier, would this be calculator active? If I asked you the thing I asked you, which is actually find the volume, definitely. So let's practice doing that. Take a minute with your calculator. Let's use Math 9 to determine what this volume would actually be. Okay? Did you guys get it?
Yeah.
What'd you get?
3.586.
Okay.
Yeah, that's what I got.
So this table got that. Let's see if you guys can confirm that, or if you want to argue with them. You like that? Okay.
This is a true statement.
Whoa, he took it to the word truth. It's bold.
What?
I should probably be in radian.
Definitely calculator active here. All right, so guys, walking around just asking, everybody seems to agree with that number. Am I right? Yes, we agree? 3.586? What's that?
I just got pi.
You bring up point number 1. So 2 points I want to bring up here as far as hopefully we're to a place where we're starting to understand what's happening and how the shape is formed. Now let's start talking about mechanics. Plenty of folks over the years understand what's happening. They can make it out of Play-Doh. They can draw it. They can, make it out of food or whatever. They understand what's going on, but then when it comes time to actually figuring out what the volume is, issues arise. Can I point out the two number one issues for handling this? Forgetting the pi, and you just saw it, Josiah, or forgetting the squared. Those are the two hugest things. People put so much effort into integrating from 0 to 1. They figure out the limits of integration or from left to right or bottom to top, and they do all that work, and they do a lot of work to figure out the radius, and they get that in there. Then maybe even they write squared on their paper, but they forget to put it in their calculator. Hey, every now and then I'm guilty of the same thing. So, hey guys, can I tell you what I do to help me with this? Before I do anything in particular on the calculator, like, you know what, let me show you what I would do here. On the calculator. If I was going to do this, I'm going to just be totally transparent. If I was going to put that in my calculator, you'll have it on your paper. Here's exactly what I would do. Maybe this will help. I'm going to go to my calculator. And so I enter it just like this. I go pi math 9. That's step number 1. I go pi math 9. So where people fall into a trap is they say, you know what, I'll just do math 9, and then I'll multiply by pi afterwards. It's so easy to forget the pi, because usually the number you get is all kind of complicated looking anyways, and you don't even realize that there needs to be times pi as well. And so I start off with pi math 9. I don't mess around with maybe forgetting the pi or maybe remembering the pi. I just automatically do that. And then I skip over my limits of integration. This is before I've done anything else. And I go open parentheses, close parentheses, squared. That way, at least I know I didn't forget the squared and I didn't forget the pi. I might mess up the radius and I might mess up the limits of integration, but at least the two things that are easy to forget, I've already put in there. And then I go back and I'm like, okay, I've got those in there. Now I'm going to go back and I'm going to say, my limits of integration were 0 and 1. And then I'll come in here in the parentheses. I'm going to insert, it was inverse cosine. Whoops. Delete. I'm going to go parentheses, and then inverse cosine of y and then I do that. So then you get your dx in there. Oh, I guess if you forget your dx or your dy, your calculator won't even let you do it. But I'm going to put that squared in there just to remind myself. It's got to be a squared radius. It's got to be a squared radius. It reduces the likelihood of me forgetting it or accidentally erasing it or whatever. So, yeah. Any questions? Okay, I'm trying to go really slow here because I want you to try to get the concept. That's kind of the main thing here. All right, well then, moving on, let's take a look at this next one. And this could be one where I'm going to have you guys try to do this one full go on your own. Draw the picture, get it set up, figure out the answer, et cetera, et cetera, et cetera. Let's think of this with this disk method. Think of this as maybe an opportunity to show what you know. Ready?
Yes. Because you gotta find volume.
Have you heard about line 5 by the interval?
It does seem to, like yesterday.
Hey, let's. Hey Ben. Sorry to interrupt. You guys are talking about interesting stuff, I know, but
No, we're all good.
let's see how you did. So from a graphing perspective, did you guys get an upside down parabola shifted up to? Something like that? So then when you think about the region bounded by that and the x-axis, I think we kind of have to think about this whole region from the left side over here to the right side, like that. That whole region right there. It's making sense? Okay. So then that is rotated around the x-axis. So let's see how much you guys are remembering. If I'm rotating around the x-axis, then what kind of a representative rectangle would need to be used? Sorry? Vertical, right? Because what is the relationship between the representative element and the axis of rotation? Got to be perpendicular. So there is a representative rectangle. That also means I'm going to be accumulating from the left side to the right side, like so. That also sets up my variable of integration. Is this going to be a dx rectangle or a dy rectangle? It's going to have to be a dx because, again, the thickness is measured on the x-axis. I want to make sure that's really clear. Do you guys have any questions why it's dx instead of dy? I'm talking about thickness, not height. Okay. So then if I was going to set this up, I'm going to write pi integral of radius squared, and I know it's going to be dx. So I'm going to set up my framework like that. I'm going to be really consistent. You guys can see the washer methods coming up, and we'll talk about that a little bit today before we go. And I'll be really consistent with this sort of framework with that as well. All right, so I got to figure out my limits of integration. I am accumulating from left to right, so I'm going to be accumulating from over here on the left side to over here on the right side. Did you guys figure out what those x values are to determine the start and stop for the accumulation? Say again?
Plus or minus root 2.
Plus or minus root 2, yep. So negative root 2 over here on the left, positive root 2 over here on the right. So as I continue to construct this, it would be negative root 2 to positive root 2. Now, as far as the radius is the distance from the axis of rotation, which is a red dot there, up to the outer edge of the region. So if you wanted to be really generic about this, what would you say about that? Like how big is that distance? How could you express that?
2 minus x squared.
Going a little further than I want you to go. Yeah, if you start on the x-axis and you move up, that's technically a y distance. So if you wanted to put a y right there, I think you could justifiably do that, but you wouldn't be done, right? You wouldn't have a completed picture of this yet. What is y equal to? 2 minus x squared. Yeah, so you could just put that in place. And I would expect that you would probably just do this immediately. Although I will say with the washer method, I think that analysis with x's and y's and what is it really, I think that really could come into play and really benefit you. So that's a good setup right there. If the calculator was active, then you'd be foolish to not use Math 9. Correct? Let's talk about the the resulting solid, I think this might be a useful thing for us to talk about. If you were going to describe the resulting solid of taking that purple region and rotating around the x-axis, how would you describe the resulting solid? A kickball? A football? Rugby ball? I think it's like sort of a football sort of thing, right? The football has like sort of pointy on the ends, right? It's round in the middle. It's not obviously not a circle, you know. I think rugby kind of the same way. Say again? A watermelon. I like that even better. We're going back to food again. Well played. Say again? A lemon? Yeah, I think you could do that too. Yeah. Hang on one second. There's a point to this. Listen, please. This could concern you. In fact, it very well likely will. Unlike a real watermelon that just kind of grows as it's going to grow, a football, if it's manufactured properly, should have symmetry, right? You don't want a football that's like really lumpy on one end and sort of flat on the other end. Do you see the symmetry in this shape? So what if the calculator was not active? What if you had to do this on paper? You could actually make this a lot easier using symmetry. Any ideas on what you could do to adjust some stuff to make this a bit easier with symmetry? Do half of it. So how would I do half of it?
So just your limits of integration, go like 0 to root 2.
Same integrand or a different integrand?
Same thing, right?
Okay, so here and there. So what's that? Isn't that exactly half? So how do I then get the whole thing? Multiply by 2.
So that would, yeah.
This would give you the exact same volume, and it should therefore be correct. Why would this be easier to do if you had to do this on paper? The 0, right? 0 with a polynomial thing, that always makes it easier. And so using symmetry about the y-axis there, getting that 0 as part of your limits of integration would make doing it by hand on paper would make it a bit easier on the end, right? So you'd have to do a little bit of work. If you were going to do this on paper, you'd have to FOIL this out and do a little bit of work. You're all kind of grimacing like, I can't do that. It might be impossible. Let's do it. Let's do it. So please try it on your paper. You've got room there. Try it on your paper. Maybe you've already done Math 9. See if you can confirm by getting the same answer. Okay? Lainey, what did you say? So we were talking about how could you use symmetry to make this easier, and the idea was this shape, whether you look at it 2-dimensionally or 3-dimensionally, has a line of symmetry essentially, right? The line of symmetry would be the y-axis right there.
Okay.
And so like this half over here and this half over here have the exact same area. So when you think about rotating it, like if I just rotated this part, that would give me half the volume. And if I rotated this part, that would give me the other half the volume.
Oh, it's because we're changing that.
And so we said, you know what, instead of starting our accumulation on the far left edge over here,
Okay.
let's start it right smack on that line of symmetry.
Okay.
0, right? At x equals 0. We'll stop over here as normal. So if I just look at this part only, that's going to give me exactly half the volume that I'm looking for. Then by multiplying by 2, that'll give me the whole volume.
Okay. So are we doing that because it makes things easier, or we're just doing it to test it out?
So both. So if you had to do this on paper, like if the calculator was not active and you had to figure out the volume, then I think using symmetry here would make it a lot easier, simply because you get rid of that lower negative root 2 limit. And now when it comes time to do the FTC1, you've just got a 0 to plug in there instead of another root 2. To me, that sounds easier. And then also to confirm, make sure that it actually all works.
Okay. Cool. Thank you.
Yep. I went ahead and foiled it out up there, which you got to foil it out before you go any further.
Oh, it's not hard. Don't worry about it.
Anyways, give you guys just another couple of minutes here to. Oh, you're good.
32 root 2 over 50.
How you guys doing? Getting this?
So, did you want us?
I want you guys to try to do it by hand. Yeah, that's what I said.
Oh, by hand. Sorry.
Math 9, yeah, Math 9 you should have been done with 5 minutes ago. What's that?
I keep getting a negative number. That's a problem.
That is a problem. Check your FOIL. Did you get the same FOIL I did? When you FOIL out the integrand there?
You'll be ashamed, Mr. Anderson. I just distributed the two. So.
I won't tell anybody.
All right, don't tell my pre-calc teacher. You might kill
Okay.
me. Or my algebra teacher.
Oh, did you?
Free algebra.
So 2 minus x squared is really 2 minus x squared is really 2 minus x squared times 2 minus x squared. You got to do FOIL. So 2 times 2 is 4. Your middles both give you negative 2x squared. That's where you get this. You multiply your last and you get that.
And then you integrate.
And then, yeah, I haven't done that part
So
yet.
if I'm doing the chain rule,
It doesn't work because the derivative of the inside should be negative 2x. Therefore, the outside factor has to have an x in it, and it doesn't. So just thank the Lord that it's not 2 minus x squared to the 20th or something like that. Not that we would do that, but squared, definitely doable.
right? Okay, that makes sense. And you integrating at 4x minus 4 over 3x cubed plus x to the 5th over 5.
Yep, and then you do your FTC one. Yep, exactly.
I did not know that.
Can I leave it like that?
Sure. Did you confirm that that's the same as what you got? Yeah, totally.
They're never with each other.
About what?
That's just like what we figured out last year. Kaylee and Cole.
Okay, guys, let's check out and see how this went. Walking around, there were definitely a little bit of issues with the algebra of like the expanding and foiling. This would be your new integrand if you did expand and foil, which you have to do. So then your antiderivative stage, we'd have 2 pi, and it would be 4x minus 4/3 x cubed plus 1/5 x to the 5th, evaluated from 0 to root 2. And then I'm going to use FTC1 and plug in the root 2, so it's going to be 2 pi parentheses 4 root 2 minus 4/3 root 2 cubed plus 1/5 root 2 to the 5th. And then I don't have enough room to plug in the 0, but it doesn't matter because I've got a polynomial and I'm plugging in a 0. And so it's just going to end up being 0, or a polynomial-like expression. So technically there's a minus 0 on there, but it doesn't really matter. If I were then, listen up please, if I were then to take the calculator and just confirm, did you guys get to that stage and see that it's the same?
I did.
Should work out.
Could you make them, like, all have a common denominator and then combine them?
So can we talk about that? This would be a really good illustration of like what you do with FRQs. So let's pretend that this was a real free response question on the AP test, or for that matter, one of my tests or some quiz coming up, and you had to do this on paper and you end up with, I mean, I know you see this and it's kind of an unsatisfying answer because you're just like, oh my gosh, and you want to do something like what Zach is saying, like, could we, the common denominator would be 15.
Right, and then I put them all together. Didn't feel like combine those different like square values by just
Right, yeah, because it'd be 2 root 2 and it would be 4 root 2. You actually could combine those and you probably could neaten it up just a little bit. But I'm going to say this. Please resist the urge to do that. What, did you do that?
Yeah, we are. 64, 5, or 215.
Sweet, that's awesome. Please resist the urge to do that because if this really were a free response question and that was the right answer, you cannot, if you keep going, you cannot possibly earn any more points. But you could possibly lose points because, oops, some common denominator issue I added wrong, whatever, some little minor thing could cause you to lose points. So stop right there. If you can navigate all the way through the end, you get it right. Obviously, that's no problem. But you're just taking an awful risk for no reward, right? You're putting like $100 on the line with no possibility of winning anything. Anyways, you guys good? Okay. Question, yeah.
So I was wondering if you're going to go about the y-axis, and
Yep.
try to find that. Can you like?
Well, so yeah, I don't think I'd ask a question like that. I probably would just give you like this half over here and do what you said.
Yeah, like I was just wondering, like, could you use both sides if you have like?
You just have to pick one side or the other.
You're not going to see that point.
Yeah. Yeah. Otherwise, the idea of radius gets kind of messed up, right?
Not have any money left or
Ladies and gentlemen, listen up, please. Listen up, listen up, listen up. Again, I know that I'm interrupting a lot of really interesting conversations. I fully acknowledge that. Sorry, but I've got to do that so that we can continue to move forward. I want to finish off our time today with just a little bit of visualization to kind of help you understand what we're going to be doing, and we'll be doing this with Play-Doh and so on and so forth in the coming days. Both of the regions that we looked at today, I would classify them as being solid, as in, like, there's no way that water could be held by either of these solids. You know, like if you think this one was like a football, and the other one, I think we said it was kind of like a bullet or a ham or whatever. This was like, you know, the watermelon. Like a watermelon, like if you think about a whole watermelon, there's no way you could orient the watermelon so that water could be held by it or go through it. Wouldn't water just like basically fall off of it? That makes sense? So what if you had a little bit of a different scenario in which, we'll talk about this a little bit more tomorrow, a lot more tomorrow in the coming days. What if you had a scenario in which you had a solid that could be reoriented in such a way that it was like a bowl? Right? So in other words, like this. You know what? I'm going to be able to illustrate this better with my Play-Doh. So check this out. What we've been doing so far is a solid object like this, right? So if you think about this object, please pay attention. If I poured water on this, if I just literally poured water right here, it's not going to hold any water, right? Water will not pass through it either. But what if I dug it out? Like this. And I oriented it like this. You see the hole in there? Now it's kind of like a cup. And couldn't I pour water in there? And water would actually be held in there. I could like drink out of it if I wanted to. Disgusting Play-Doh water. Yes?
Very nutritious.
So now please, this could be a little bit of a game changer, right? Additionally, you could also have a shape like this in which the shape couldn't necessarily hold water, but water could pass through it because there's a gigantic hole right in the middle of it. Okay? So in both of these cases, I would say that whether we have this shape here where you can like see through it, or where it would actually, well, wouldn't hold water yet. There we go. Or here where it would actually hold water like a cup or a bowl or something like that. In these situations, we got to think a little bit differently, and that's where we are going to use what's called the washer method. And I think I'll show you this real quick. I guess I got it up here. When you guys see the word washer, what do you think of? Think of the washing machine at home?
Think of the washer.
So, guys,
Eagles, today is Alpha Tuesday.
what you should be thinking about is instead of a washing machine where you wash your dishes or your clothes, you should be thinking of the hardware store washer. You guys see the hardware store washer taking shape here? And so instead of using discs, which are solid, you know, like we've been working on to create a solid shape, we're going to be using these little washers to create a shape with a big hole in the middle, right? One in which you could have water being held, or water could just like pass through it, or you could see through it, right? So this is a clear washer method, right? Because I can see through it. This is also a clear washer method because water can be held by it. That make sense? Okay. So then let me just give you a brief tutorial just to kind of get your appetites wet for lunch and class tomorrow. How does this work? Check out this formula here. I'll draw you some nice pictures tomorrow. But check out this formula. Hey, if your eyes are not on the screen, they're on the wrong spot. Please check it out. See the formula, right? What if I took this integral and using those properties that we've looked at in the past, what if I split it up? Wouldn't I get pi? Let me give myself a little more room here. I would get pi integral from a to b of big R squared minus pi integral from a to b of little r squared. When I look at either one of these, isn't this exactly like what we did today? pi integral r squared. And isn't this exactly like what we did today? So if you can picture how we're going to create this hole, is we're going to create a big solid shape, and we are going to remove a small solid right out of its middle. Therefore, can you picture how that would create a bowl? If you created a solid bowl in which no water could be in, kind of like I did with the Play-Doh, but then you scooped out the middle, wouldn't that then create maybe like a cup or a real bowl? Yeah, Riley.
Then why would the B and A not be different for the smaller one?
We're still integrating over the same domain. We'll get into the details tomorrow. Don't worry too much about the details right now. I'm more concerned that you get the concept of like big solid with little solid pulled out. Does that make sense? It has to do with the perpendicularity thing, right? Because the representative disk might be taller or shorter, but we're going to still integrate over the same region. From x equals 1 to x equals 5. It's going to be the same for both solids. So, yeah. Hey, have a great day. See you guys tomorrow. Was there a so on that one? No? Okay.
Just like a
Oh, you're going to?
sense.
Gotcha.